Imagine a world where objects can be in multiple states at once, where particles are intertwined in ways that defy distance, where the very act of observation shapes reality. This is the strange and counterintuitive world of quantum mechanics, a theory that has revolutionized our understanding of the universe at its most fundamental level. At the heart of quantum mechanics lies the concept of superposition. Unlike classical physics, where an object exists in a single, well-defined state, quantum mechanics allows particles to exist in a combination of multiple states simultaneously. This mind-boggling idea is exemplified by the famous thought experiment of Schrödinger's cat, where a cat in a box is both alive and dead until observed. Equally bizarre is the phenomenon of entanglement, where two or more particles become linked, even across vast distances. This connection is so strong that measuring the state of one particle instantly determines the state of the other, regardless of the separation between them. Einstein famously referred to this as spooky action at a distance, highlighting its seemingly paradoxical nature. Further challenging our classical intuitions is wave-particle duality. Light, for example, exhibits both wave-like and particle-like behavior. It can diffract through narrow slits like a wave, yet it can also interact with matter as discrete packets of energy called photons. This dual nature of quantum objects has profound implications for our understanding of the very fabric of reality. These fundamental aspects of quantum mechanics, superposition, entanglement, and wave-particle duality, paint a picture of a reality far stranger than anything imagined in classical physics. They challenge our everyday experiences and force us to reconsider the nature of reality itself. The quantum puzzle, macroscopic objects, and the collapse of superposition. While the bizarre predictions of quantum mechanics have been experimentally verified countless times in the microscopic realm of atoms and subatomic particles, a fundamental question arises: why don't we observe these strange quantum effects in our everyday macroscopic world? Why don't we see objects existing in multiple states simultaneously, or cats being both dead and alive? This discrepancy between the quantum and classical worlds hinges on the concept of wave-function collapse. According to quantum mechanics, the wave function of a particle, which describes all its possible states, collapses into a single definite state upon measurement. This collapse is what seemingly forces the quantum world into our familiar classical reality. But what constitutes a measurement in this context? And why do macroscopic objects composed of billions of atoms, each obeying quantum rules, behave classically? These questions lie at the heart of the measurement problem in quantum mechanics, a puzzle that has perplexed physicists for decades. Recent experiments have attempted to probe the boundaries between the quantum and classical worlds by creating and manipulating larger and larger quantum objects. Researchers have successfully placed molecules containing hundreds of atoms into superposition states, demonstrating that quantum behavior is not limited to the subatomic realm. However, as objects grow larger, maintaining their quantum coherence, the delicate interplay of different possible states becomes increasingly difficult. Interactions with the environment, such as collisions with air molecules or thermal vibrations, tend to destroy this coherence, leading to the familiar classical behavior. Despite these experimental advancements, the question of why and how wave function collapse occurs remains unanswered. This unresolved puzzle points towards the limitations of our current understanding of quantum mechanics and hints at the possibility of a more fundamental theory waiting to be discovered. Pushing the boundaries theories beyond standard quantum mechanics. The extraordinary success of quantum mechanics in explaining the microscopic world is undeniable. However, the theory's inherent strangeness, especially the measurement problem and the unclear boundary between the quantum and classical realms, has led many physicists to believe that it might be an incomplete description of reality. This has given rise to a plethora of interpretations and extensions of quantum mechanics, each attempting to address the theory's shortcomings and provide a more complete picture of the universe. These theories, while still speculative, offer tantalizing glimpses into what might lie beyond the standard model of particle physics and our current understanding of reality. Some of the most intriguing theories include objective collapse models, which propose modifications to quantum mechanics that force wave function collapse to occur spontaneously, independent of any observer. Others, like quantum gravity theories, attempt to unify quantum mechanics with Einstein's general relativity, seeking to describe the universe at its most extreme scales, from the Big Bang to the singularity at the heart of a black hole. Still, other interpretations, such as the many worlds interpretation, offer a radical departure from our intuitive understanding of reality. This theory suggests that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome of the measurement. Finally, there's superdeterminism, a controversial interpretation that challenges the very notion of free will. Superdeterminism posits that the universe is fundamentally deterministic, with all events, including our choices, predetermined since the beginning of time. Each of these theories, though speculative, offers a unique perspective on the limitations of quantum mechanics and the potential for a deeper understanding of the universe.